ओके अब चलते हैं स्टूडेंट्स अल्टरनेटिंग करंट 14 here we'll be discussing only a pure resistance and a pure inductor in series and alternating EMF, and what we'll find out what is the total resistance offered due to these two, that is the impedance, and how whether the EMF lags behind the current or ahead of the current. Since we have already discussed series RLC circuit prior to this 15, we have already discussed resistance, inductance and capacitance in series. We have already discussed this. Resistance, inductance, capacitance in series. So all through the current is same. The direction of current and the maximum value of the current. So, but the only difference was in case of inductor, the current was lagging behind. And here in case of a capacitor, the current was ahead of the EMF. Here the current was lagging behind the EMF. And with this as the applied EMF, where the resistance of this was R, the resistance offered by this coil to this circuit was called inductive reactance. The symbol was XL, it was omega L, 2 pi nu L. It depends on frequency. If nu increases, this part will increase. Similarly, the resistance offered by the capacitor to this circuit was XC, 1 by omega C, that is 1 by 2 pi nu C, depends on nu. So this nu in the denominator, so nu, if nu increases, this decreases. If nu decreases, this increases. And the total resistance offered was symbolically written as Z, R square plus XL minus X is square root of that. This is the total resistance offered. It was called the impedance. Now in the present case, we don't have a capacitor. So just use this expression. From this expression, eliminate this part, remove this XC part because it is not there. That's a data. Remove this XC part. Use this expression and remove this XC because it is not there. So it is as simple as that. So let us begin. In AC 13, where we discussed series LCR circuit, the impedance was found out to be Z was equal to R square plus XL minus X square, square root of that. But in this case, we don't have a capacitor. We have only R and L. The resistance offered by this is R. The resistance offered by this is equal to XL. That is equal to omega L, called inductive reactance. Now, from here to here is the voltage across the resistor. From here to here is the voltage across the inductor. So this voltage plus this voltage is same thing as this voltage. Now we know for a resistor, and the current and voltage, they are in phase. This we had derived in previous lessons. For a resistor, only resistor with alternating EMF, if this is the applied EMF, our current had come out to be I was equal to I naught sin omega t. Omega t, omega t. Voltage and current are in phase. So, and that is how I am showing here. The voltage across the resistor and the current, they are in phase. And for an inductor, look, they are in series. So the current is same. Only the direction of voltage has to be considered. For an inductor, I had derived previously. For an inductor, a circuit containing an inductor and alternating EMF, for this the current was derived as I is equal to I naught sin omega t minus pi by 2. Current is lagging behind the EMF by pi by 2. Or you can alternately say the EMF is ahead of the current by pi by 2. That is what you can say. This is lagging behind this by pi by 2 current, or you can say the EMF is ahead of the current by pi by 2. So that understanding will apply here. EMF means the voltage across the inductor represented as VL is ahead of the current by pi by 2, that is equal to 90 degree. So if you look at the phase diagram, means the vector diagram, using this you can straight away find out X is not there, so no capacitor, therefore X is equal to 0. So from this your impedance is Z will be just R square, this is 0, XL square, square root of that, square root of that, where XL is equal to omega L 2 pi nu L, the frequency of the applied voltage. This frequency is the frequency of this applied voltage across R and L. For India, this nu is equal to, this nu is equal to 50 Hertz in India, 50 Hertz. Now look at here. And we also had derived in lesson 13 the tan phi. Tan phi was XL minus XC over R in alternating current lesson 13. Since XC is not there, so remove this XC part. So we have only XL over R. Therefore, tan phi is XL over R, that is omega L over R. So that is omega L over R. Or if you look at from this diagram, the phasor diagram, look, voltage across R. If you compare this and this, angle between VR and VL is 90. So VR is to this side, VL is to this side. So the resultant of this, VR and this VL, using vector addition, this is one vector, this is another vector, so this is the parallelogram, so this is the resultant. So this is your phi. So tan phi is equal to AK over OA, and that is what I am showing here. Tan phi is equal to AK over OA, and AK is same thing as OL. AK is something as OL by OA. Tan phi is perpendicular, sorry, I have made a mistake here. Tan phi is AK over, in this diagram, tan phi is AK over OA, and not OK, right? So, and OL is nothing but, OL represents the voltage across the inductor, and OA represents voltage across the resistance, and any voltage is equal to current into its resistance. The maximum current through this is I naught. Because both the elements, both this and this, they are in series. So I naught cancel, so XL over R, and XL over R, XL is omega L over R, so tan phi is omega L over R. So it is positive. Therefore, the conclusion is EMF leads the current by, from here, phi is equal to tan inverse omega L over R. If you know the value of omega, that is 2 pi nu, if you know the frequency, and if you know the value of L and value of R, if you put it here and take the tan inverse, you find out the phase angle phi, the angle by which the EMF, the resultant EMF, leads the current, because current is this way, leads the current by what angle, you can find out.